Hello everyone, welcome back to the class of differential equations and matrices. And this time we are working on section 4.4 about so-called undetermined coefficients. And we do have the generalized way to handle the situation. This is the second order linear non-homogeneous differential equation with constant coefficients. A, B, C are numbers. Okay. So to handle this type of differential equation, first you consider the corresponding homogeneous differential equation and denote the solution as y sub h. And then in the second step, you want to find out a particular solution. And the particular solution, it is denoted by y sub p. And for the particular solution, there are three cases to consider. The right-hand side is a polynomial, the right-hand side it is an exponential, and the right-hand side involves with trigonometric functions. And we already did one simple example. It is for the right-hand side as linear polynomial. And I said if that is the case, the particular solution should be assumed as a linear polynomial too. Okay. And accordingly, if the right-hand side it is a quadratic polynomial, you assume the particular solution it is a quadratic polynomial. So I do have another example fitting for the case of polynomial. Actually, it is pretty much the same example like we did a moment ago. It's a second order linear non-homogeneous differential equation with constant coefficients. Okay, and the right-hand side certainly it is operated. Now it is a quadratic polynomial. So step one, first we consider this as a homogeneous differential equation. I suppose you know this part very well as a homogeneous differential equation. Okay, so I denoted the solution as y sub h, and which is really I just literally I copy and pasted from the previous example. Okay, and then the second step, we are going to generate a particular solution, and I'm seeing the right-hand side as a quadratic polynomial. So accordingly, you want to assume the right-hand side as a quadratic polynomial. And you do want to assume the complete terms of the quadratic polynomial. So I'm having at squared plus bt plus c there. Okay, the complete terms of quadratic polynomial. And then A, B, C, these are unknown coefficients. Or if I use the phrase as for the textbook, these are indeed the so-called undetermined coefficients right here. Which means we really need to find out A, B, and C. So the way to find out those undetermined coefficients, okay, make sure you assume the particular solution in the form correctly. And then you calculate the derivative from there. It's a quadratic polynomial, so yp prime, it is 2at plus b. And the yp double prime, it is 2a, right? Then you are going to put y sub p prime, y sub p double prime back into the original differential equation, the right-hand side. Because there's nothing to plug in, the left-hand side. I mean, there's nothing to plug in for the right-hand side, right? So I plug in everything together. It may look pretty much complicated, but anyway, make sure you do recognize whatever the thing that you may have. Especially don't let the notation ABC to confuse you. I'm seeing ABC as numbers, so it is a quadratic polynomial. So I arrange the quadratic polynomial into the descending order. Usually this is the standard approach, how we handle polynomial. Usually we put the polynomial in the descending order. So starting from t squared, then t, then constant. Okay. So I'm having the term with t squared and the coefficient with t, and then the constant. And again, this the 3-bar notation may look a little weird, but anyway, in some way it is no different from 2 bars. It just means equal, okay. I meant to say they should, the left and right, they should match exactly. So indeed, there are not a lot of ways to match exactly because A, B, C, they are all unknown. They are undetermined coefficients. So what we can do here is we just match the corresponding coefficients. So I said the coefficient of t squared will have to match 3 there. And also another interesting here is about t. Looks like there's nothing to match that t, but do consider there's t to the right too. It is 0 times t. So I said negative 2a minus 2b, that's 0. And then finally, whatever the thing is, it has to be a constant, right? And it will have to match that negative 1 from the right hand side. So I'm seeing this is a system of 3 equations with 3 unknowns. We should have a unique solution. At least we should have one solution here, right? And so A, this is what I got from the first equation, negative 3/2. And then you can solve for B from the second equation, B is 3/2. And then finally you put A and B into third equation. I'm getting C as negative 7/4. Negative 7/4. So what I'm saying here is the particular solution. It is a quadratic polynomial. We do have an actual solution for the differential equation here. So step 3, it just simply says in general, the general solution always can be arranged as the homogeneous solution plus the particular solution. So I just repeated them. I copy and paste. Hopefully everything should be fine. This is about the way how we handle the right hand side. When the right hand side is a polynomial, you want to assume the particular solution is a polynomial of the same degree. Okay. Example 1, example 2, actually they both fit for the same case. Right hand side is a polynomial. How about let's move to the second case. What would happen if the right hand side it is an exponential function? Well, when the right hand side it is an exponential function, basically you want to assume the particular solution it is of the same kind of exponential function and with a different coefficient. So example 6, I have on my notes, really it is in a very somewhat it is related to the other one, okay. The differential equation part, the left hand side is always the same. I just updated the right hand side. No polynomials. It is an exponential function. So for completeness sake, I still listed out step 1, step 2, and step 3. So for step 1, it is still from the previous example. I'm not going to repeat a lot. I just want you to know the characteristic. I think that should be fine why there's a red curve here. Okay, we'll figure out this later. And at least I want to make sure you know the homogeneous solution as we did many times. It's a linear combination of those two exponential functions. 2 and the negative 1, those are the roots of the characteristic quadratic equation. Okay. And the next part, step 2, it is the big one for this section. We are going to assume the particular solution. It is the same kind of exponential function. The kind of exponential function I'm talking about here, it is e to the negative 3t. So the same kind, it must be e to the negative 3t again. Certainly it may carry a different coefficient. So I said that the coefficient a. I hope you know a is the so-called undetermined coefficient, right? So we try to find a value for this a. And like we did before, I calculated the derivative. I calculated the second order derivative because of the chain rule, okay? This also has a chain rule here. Now it has negative 3 in the front, and the chain rule again for the second order derivative, I got two negative 3's. Negative 3 times negative 3, that's 10 to plus positive 9 here, okay? And then I get everything, yp double prime, yp prime, yp into the original differential equation right here. And still, let's pay a little more attention to the left-hand side. We have the common factor of e to the negative 3t, right? So the coefficient of 9a minus negative 3a, that's really plus 3a. And the 2 minus 2a, they all can be combined. And when they combined, we want to match the right-hand side with the coefficient 2. So I got reached to this point. So indeed, in this case, I'm getting this a has to be 1/5. A has to be 1/5. So I'm saying the particular solution in this case, it is 1/5 times e to the negative 3t. A differential equation has many solutions. And this differential equation we consider here, it is non-homogeneous. Still, it has many solutions. But in step 1, we just figured out all the homogeneous solutions are in the linear combination of these two. And then we do have a particular solution. Then step 3, there's no stranger for step 3. You just add the results from step 1 and step 2 together. Step 1 and step 2 together. And that is our final answer. The general solution is y sub h plus y sub p, and add those two functions together. So this is the study of section 4.4. We will have a little more about the 4.4. So see you next time, and thank you for watching.